All right, let's dive right into this explainer and explore the invisible forces that literally power our entire world. From massive, sky-splitting storms all the way down to the sleek, silent device you're holding in your hand right now, electricity and magnetism are absolutely everywhere. Today, we're going to unpack a really comprehensive overview of these topics, specifically drawing from Chapter 7 of the KSSM Science Form 2 syllabus. It is a super fascinating journey into the physics that shape our daily reality, so let's get into it.
So, I'm sure we've all felt it, right? That sudden, tiny zap when you reach for a metal handle after walking across a rug. It's a little surprising, sometimes even a bit painful. But what exactly is happening there? Why does your body suddenly turn into a miniature lightning bolt? Well, the answer lies in a little something called electrostatic charge.
And here's the wild part. The friction between massive storm clouds and the surrounding air transfers electrical charges in the exact same way your shoes rub against a living room carpet. It's literally the same physics, just on a wildly different scale. That friction causes a giant attractive force between the Earth and the sky, resulting in the spectacular lightning strikes we're all familiar with. It's just stationary energy, building up until it just has to jump.
To wrap our heads around these incredible phenomena, here is our game plan. 1. Sparks and electrostatic charges. 2. Unlocking Ohm's law. 3. Series and parallel circuits. And 4. Magnetism and electromagnets. Starting with Part 1, Sparks and electrostatic charges, let's unveil some stationary energy.
So electrostatic charges are simply electric charges that are not moving. They're just stationary. You see, our universe is made of tiny particles, and these particles have charges. The positive charges are called protons, and the negative ones are electrons. When two different insulating materials rub together, like a plastic comb and a wool cloth, for instance, only the negative electrons jump ship. The positive protons stubbornly stay put. The object that gains those extra electrons becomes negatively charged, creating an imbalance. And the golden rule of this invisible world, like charges repel each other, and opposite charges attract. We call that push and pull the electrostatic force.
Now, if you're wondering how scientists actually measure that invisible imbalance, this setup brilliantly illustrates it. This is an electroscope. When a charged object is brought near the top plate, those charges travel down the metal rod. And because like charges repel, that delicate little gold leaf at the bottom gets pushed away from the rod. It is a beautifully simple, visual way to prove that these invisible forces are actually there.
Moving right along to Part 2, Unlocking Ohm's Law, the rules of electrical flow.
Okay, once those charges start moving, we need new terms to describe them. Think of a flowing river. Current, represented by the letter I, is simply how much water is rushing past a specific point every single second. In electrical terms, it's the rate of flow of electric charges through a conductor, like a copper wire. We measure this flow in a unit called amperes, or just amps for short.
But, what makes that river flow in the first place? Sticking with our analogy, the voltage, represented by V, is like the steepness of a waterfall pushing that water forward. It's the potential difference that forces the electric charges to move from point A to point B. Without voltage, there is no push, and the current just sits there. We measure this vital pushing force in volts.
And finally, we have resistance, represented by R. Resistance is like the rocks and boulders sitting in our river, slowing the flow of water down. Every single material has some level of resistance to electricity. And this depends on a few things: the type of material, the length of the wire, its diameter, and even its temperature. For instance, a long, thin, hot wire has way more resistance than a short, thick, cold one. We measure this resistance in ohms.
To ground this theory in the real world, here is what these concepts look like in a laboratory setting. On the left, we've got standard dry cells, basically what you and I call batteries. These are your source of voltage. They give the push. And on the right is a voltmeter, the actual instrument engineers and students use to accurately measure that potential difference.
Now here is the real game changer. These three characters, current, voltage, and resistance, don't just exist randomly. They have a strict, inseparable mathematical relationship known as Ohm's law. Ohm's law basically tells us that the electric current flowing in a circuit is directly proportional to the voltage going across it, provided the temperature remains fixed. The core equation you absolutely need to remember here is V equals I times R. Now, if that math looks a little intimidating, no worries at all. Just use this brilliant Ohm's law triangle cheat code. You just draw a triangle with V on top and I and R on the bottom. Simply put your finger over the letter you want to find, and the formula reveals itself instantly. Want voltage? Cover the V, and you see I and R next to each other, so I times R.
Need to find current? Cover the I. You see V over R, so it's V divided by R. It makes solving complex circuit problems an absolute breeze.
Part 3. Series and Parallel Circuits. Pathways of Power.
When you're building a circuit, you basically have two main choices for how to lay the track. A series circuit is the simplest route. It forces all the current through one single continuous loop. Every component is connected one after the other. A parallel circuit, on the other hand, is kind of like a highway with multiple exits. It separates the current into several different parallel paths, each containing its own electrical components.
And looking at these approaches directly reveals their real-world consequences. A series circuit has a pretty major flaw. If just one single bulb breaks, the entire loop is broken, and every single light goes dark. Think of those really frustrating old holiday lights. Because of this, engineers heavily rely on the parallel circuit. By giving the current multiple paths to take, a parallel circuit lets you turn off your bedroom light or have a single bulb burn out without blacking out your entire house. It's a much more robust design.
All right, our final section, Part 4, Magnetism and Electromagnets, the ultimate tag team.
Let's quickly establish the ground rules of a standard natural magnet. Magnets naturally attract specific materials, namely iron, steel, cobalt, and nickel. They always have a north pole and a south pole, and just like electrostatic charges, opposites attract while likes repel. But the really fascinating part is the magnetic field itself. This is a totally invisible area of force around the magnet. The field lines always flow from north to south, and the closer those lines are to each other, the stronger the magnetic force is at that specific spot.
But here is where physics gets really fun. We know about electricity flowing through wires, and we know about magnetic fields. What happens if we combine the flowing electricity we just learned about with these magnetic fields?
You get something called an electromagnet. By simply wrapping a conductive wire into a tight coil, called a solenoid, and running an electric current through it, you actually generate a magnetic field. You've created a magnet. But unlike a regular chunk of iron, this is a magnet that you can turn on and off just by flipping a switch. It only has a magnetic effect when that current is flowing.
And the absolute best part of an electromagnet isn't just the on-off switch, it's the volume dial. You can totally control its power. If you want a stronger magnetic field, you simply crank up the current flowing through the wire. Or if you want to make it stronger without adding more power, you just increase the number of turns in your wire coil. It's an incredibly customizable force.
And this controlled, invisible force is literally the bedrock of modern engineering. Because we can scale its power on demand, we use electromagnets everywhere. We use massive electromagnetic cranes to effortlessly lift tons of scrap metal. Your headphones and loudspeakers use tiny electromagnets to change electric current into the music you hear. But perhaps most amazingly, this exact same invisible force allows massive passenger bullet trains to literally levitate off their tracks, eliminating friction and rocketing forward at breakneck speeds.
From a tiny spark on a doorknob to trains floating in midair, the physics outlined in Chapter 7 are truly foundational to our modern world. So the next time you turn on a screen, hear a speaker, or even flip a light switch, remember the incredible, invisible dance of electrons and magnetic fields happening right in the palm of your hand. It kind of begs the question, right? What other invisible forces are shaping our world right beneath our notice? Thanks for joining me on this explainer, and keep learning.